on how the rest of this class is going to go. We meet one more time on Tuesday. Some of you have kind of, I see half of us have figured out that there's no more quizzes. So, we will talk, the test will be on our finals night, which is a week from this coming Tuesday, so that's in 12 days. And that's just exam 4, it's not a final. Steve's like, what? Final?
We thought we had class on Thursday, that's all.
No, it's a reading day. So you're supposed to be home reading with your slippers on, fireplace going, and all that kind of stuff, with your penthouse, with reading, okay? All right, and that's terrible. All right, I haven't seen one since I was in college, but anyway, So we will cover a little bit of chapter 13. You got to see the wave equation. You got to see the wave. You did it in lab. Didn't you do springs in lab going up and down, simple harmonic motion? Yeah, so we'll, just a little bit on that. We'll be on the 13th. There's no more homework assignments besides the one I kind of slid in today, the last one, assignment 13, or 16. And so we're going to cover chapters 10, 11, and we covered 10 on Tuesday. We'll cover chapter 11 today. Okay? And so for those of you that are in the other room taking the test, that are my video class, you will come in here on in 12 days with them at 5:45 to take the final. Okay. All right, good. So we got that all taken care of. Now, let's talk about heat. Okay? Let's talk about heat. Now, we do it a little bit different in physics because you chemistry people use calories and kilocalories and all that. Which is a good unit of energy because 1 calorie, 1 small calorie is how much energy is required to raise 1 gram of water 1 degree. Okay? Well, we're going to raise 1 kilogram of water 1 degree using 4,186 joules. That's the way we do it in physics. Okay, we make it harder. All right, chemistry is nice and easy, 1 to 1. All right, but in ours, we say that the specific heat of water, which we'll get to a little bit later on, is equal to 4,186 joules per kilogram per 1 degree. So in other words, 1 little calorie. Now heat. One thing that makes me a little bit nervous about being videotaped is somebody who really knows this stuff might actually see this. But anyway, and go, that's wrong, what he said. So I hope this isn't wrong. But basically, heat is is the transfer of energy of one thing to another. Remember, the temperature of something is the way we measure the internal kinetic energy that it can give up. All right? Basically, the internal kinetic energy of something, though, is this. If it's at rest. You've all seen this before. This is the most famous one of the most famous equations of all time. But anyway, how much internal energy something has is actually equal to this. But the heat or the temperature is how much energy it has that it can give away, all right, type thing, okay, rather easily. It's how much and then heat is the flow of that energy. All right, so you all know 1 calorie, okay, which actually equals 4.186 joules, okay? All right, and then we also, just for kilocalories, something like that, is equal to 1,000 calories, which is actually equal to the 1 big CAL. That's like an American thing that we use. In other words, how many calories something has. Okay, the big C. Do they do this in China? They probably have it in joules, right? Yeah, so if you go to China and get a pop, it'll say, oh, this has 10,000 joules, okay? You might go, wow, it's fattening. But actually, it's just 3 big calories or whatever. So I guess that would be a Pepsi 3 instead of Pepsi 1 or 0 or whatever. But anyway, so you got these calories. All right, so let's see. So if somebody goes and they eat, which actually equals 4,186 joules. Okay? So let's say somebody goes to a party. This lady goes to a party. Oh, but before I get to that, which has more energy? 5 chocolate chip cookies or dynamite, TNT, with the same mass as the 5 chocolate chip cookies? Which has more energy? Okay, you're going, well, if you had asked me when I was in 5th grade, I'd have said, well, the dynamite, of course. But now that I'm supposed to think about it, sounds like a trick question to me. Therefore, I'm going to go with the cookies, even though I have no idea why. Okay? Okay, so that's what we're doing. All right, you're right. It is the chocolate chip cookies, okay? The reason that we don't blow things up with chocolate chip cookies is because they release the energy so slowly, all right? In other words, to get the energy out of the chocolate chip cookies, I got to eat them, I got to digest them, turn that chemical energy into work energy, whereas that transference of energy from chemical to explosive, to where it's actually the reaction goes so quick that it moves faster than the speed of sound, so therefore it compresses the air, which causes the explosion. All right, things that react very, very fast like that may not have more energy, they just react faster. Okay, and so you can do the same amount of damage with dynamite with chocolate chip cookies. All you got to do is give it to a 17-year-old boy, feed him 5 chocolate chip cookies, and hand him a sledgehammer. Okay, and he'll go, and however much energy was in those chocolate chip cookies, if he swings that sledgehammer, he'll do some serious damage. All right, so let's say this girl goes to a birthday party, and she eats some cake. All right, and the cake said 200 calories, big C. She was 200 calories of cake. Okay, and immediately she goes after the party, she goes to the gym and gets on a stationary bike. Okay? And she exerts this much power. The average power of the bike then is 200 watts. Now, what are watts actually? What are watts? What's the measurement for watts? What is it? Joules per second. Right? So it's the amount of energy. So in other words, she's burning. This machine, this thing will burn off 200 joules per second. Okay? So we want to know how long does she need to ride that bike to burn off these small little 200 calories. By the way, how many calories does the average human need to eat to sustain themselves per day? Well, it depends on a lot of things. It depends on your size, your initial weight, and all that kind of stuff. But for the most part, it's about 2,500 or so. Is about what you need. So that's why I tell my wife. 1 bottle of Fat Tire is 300 calories. I could have 7 beers a day and a vitamin pill, and I'd be perfectly happy. Okay? That'd be a great diet. 7 beers and a diet pill, or and a vitamin pill, and you got it. That won't work. So, because you need your nutrients and stuff like that. All right, which you can get from the vitamin. But anyway, you need about 2,500 to really kind of sustain yourself. 2,200 to actually go on a diet. There's only one way to diet, and that is you take in less than you burn off. That's it. There's no other tricks. There's nothing else. You just got to take in less than you burn off. Now, just for general knowledge, in the military, those meals, those little brown bag meals that the soldiers eat or the Marines eat when they go out in the field and stuff, each one of those contains they get 3 of them, and each one of them contains about 3,000 calories because they're doing a lot of, you don't eat all of them. First of all, you can't stomach them for a while until you get really hungry anyway. But anyway, so how much time? Well, this 200 calories times 4186 joules per 1 calorie. So that cancels. And so we wind up with 8.37 times 10 to the 5th joules of energy that she needs to burn off at 200 joules per second. Okay, so it's going to take a while. It's going to take a while because that's a big number. What is that? Is that 837,000 joules at 200 joules a second? Oh my gosh. She's only burning how many joules a minute? Well, quite a few. 12,000 joules a minute. So eventually she'll get down there. So it comes down to, you divide this by 200 joules per second. Those cancel, that flips up, and you wind up with a pretty big number of seconds. Yeah, it's a bunch of seconds. It's about 4.19 times 10 to the third seconds, which comes out to be about 1.16 hours. So she's going to be on that thing a long time. I suggest she put it on hills, okay? So it'll burn it off. Because when we have bad weather, and I use a treadmill, I like to turn it over to, you used to be able to turn them over. If you went over 1,000 calories, it would turn over and go back to 0. But now that goes all the way up to, I'd have to go for 10,000. I can't do that. All right. Okay, so that's kind of the first little thing. We're looking at the energy that is used. Heat is energy. Well, yes, heat is energy. Okay. All right. Now let's talk about specific heat. Okay. Two things you need to know that are happening when we add energy or when we add heat to a system, which is energy. First thing is you're increasing the molecular kinetic energy. Okay. So those molecules in there, just like the heat in this room. Those molecules are flying around here pretty quick. We'd like for them to slow down a little bit, okay, because it is warm in here, and we all came in from the cold and everything, so that's sleep-inducing. And then the second thing that happens is if you keep adding heat, then those molecular bonds, those chemical molecular bonds really start vibrating a lot, and then they start to break down, they break apart. And so what happens then, if you have a nice lattice structure that starts to break apart, that like ice, what happens when it gets too much energy? It turns into liquid, which then that starts to break down, that turns into steam, gas, right. Okay, so those are the two things that happens when you add energy to the system. Now that second thing I just talked about is what we call the latent heat of fusion. Fusion for going from solid to liquid, and vaporization is from when it goes from a liquid to, or from steam to a liquid, or vice versa, the other way around. Okay? And so the specific heat is something you all had. How many of you have had chemistry and know about specific heats and all that kind of stuff? Okay, and then there's one or two going, never had it, so you better tell me. Okay, so specific heat is this. It's just the specific heat of water. For in chemistry class is 1 because it's how much energy it takes. It takes 1 calorie per 1 calorie equals raising 1 gram of water 1 degree Celsius. Okay. Well, the specific heat in joules is this way for water. Specific heat of water is equal to 4186 joules per kilogram degrees centigrade. Okay? In other words, it takes 4,186 joules of energy to raise 1 kilogram of water 1 degree. All right? Let's talk about what this means, though, in something that might be more familiar. The specific heat for aluminum, yes?
So that symbol is specifically
C, yes. Yeah. What is it in chemistry?
Yeah, it's delta H. It's
Delta H?
That's how you measure
Is it a small h or a big H?
big H. It's a big H.
It's big H? Oh, we use C. In this club, we use C for specific heat, okay? Because that H is dealing with calorie stuff, right?
I guess. I don't know. I just know that it's not a C.
It is not a C, okay. You guys also use little h for frequency, don't you? Yeah. Sure. All right. Chemists. They're just physicists who don't like math. That's basically, no. Kidding. All right, so CAL, so the specific heat, now that we got that cleared up, the specific heat for aluminum is 920 joules per Kelvin. And the specific heat for like copper is 390. Which one's easier to heat up of those three? Which one will get hot really quick? Yeah, the copper, because it's got the smallest specific heat. That is why on nice fancy, or not even that fancy, but that is why on nice fancy pots and pans, they've got a copper bottom. They've got a aluminum sides maybe, or stainless steel. Stainless steel I think is 1220. The C for steel is around 1200 I think. So they'll have the stainless steel sides and the stainless steel handles. This gets really hot, and the stainless steel just gets warm. So you can pick it up without hot pads maybe. Don't try this at home though. Because first of all, I don't know, it could be some chintzy material that heats up really fast on the sides. But anyway. So this is why they build them that way. So because the copper is a good, and this also means, notice the difference. Water is a good insulator of heat. In other words, it cools things off quickly. But that's why they use water to cool off those rods in a nuclear reactor. Fill it with water, they cool off pretty quick. All right, as long as Homer remembers to flick the switch. But anyway, and then copper is a good conductor, and it's also a good conductor of electricity. Why? Why is it a good conductor of heat or electricity? Same thing. Materials that are good conductors of electricity are also good conductors of heat. Normally, I'm sure they've got some that aren't, but anyway. But for the most part, why is that the case? What makes a good conductor? Yeah, ability to transfer, so therefore you got to have, copper is like Southwest Airlines, okay, for the electrons. They're free to move about, okay? You got all these free electrons, right? Remember that? They told you that in chemistry? Because the different energy levels and stuff. So you got all these free electrons, as long as they're impelled to move, which they will be. In other words, things will move from one hot, got a question, quick question. Do things move from, does heat flow from hot to cold or from cold to hot? All right, so one more time. Does it go from hot to cold or cold to hot? Which way does the heat flow? Hot to cold. More energy goes to fill up the less energy things, okay? Sucks up the less energy. So when things are hot, they've got more energy for the most part. But remember, size matters, okay? The internal kinetic energy of something, if it's huge, in other words, the cold water, you need a lot of water to cool off something like a flaming red little ball of copper. If I drop it in just a thimbleful of water, it's not going to cool off much. But if I have a bunch of water, it'll and cool off rather quickly. Okay, so things that are good conductors are also good, of electricity are also good conductors of heat. And heat flows from hot down to the cold. Okay, good. So we got the big ideas down. All right, so now, let's take a look at, is it calorimetry? How do you say it? Yes, say it one more time. Yeah, calorimeter. Or what is it when you're doing it? I can never say it right. Calorimetry, right? What? Calorimetry, that's it. Calorimetry. There we go. Got it. It's chemists. Anyway, all right. So let's take a look at that. All right, now that I've Made a fool of myself on national television. Here we go. So using the specific heat, the amount of heat, and we're going to find the specific heat of copper here. Here's our thing. Q, which is our heat, is equal to the heat that we're going to, that's going to change its temperature, is going to equal the mass of the copper times the C of the copper times its change in temperature. Okay? And here's our problem. Here's what we're going to do. Here's how we're going to do this. We're going to that thing. Okay? We're going to find the C of copper, and we'll take the mass of the copper is equal to 0.15 kilograms. Okay? And now what we're going to do is we're going to heat this little sample of copper up until it reaches an equilibrium temperature with, it's like in a little test tube or something that's at 100 degrees Celsius. Okay? And then we'll let it sit there for a while. So if it reaches equilibrium, how hot is it? What's its temperature of the copper? It's 100 degrees, right? So it's at 100 degrees. So its initial temperature is its T naught is equal to 100. Okay? And then what we're going to do is quickly take that thing out, drop it into this little aluminum cup with 0.2 kilograms of water in there, wait for it to reach its equilibrium temperature, which, did you all do this in lab?
Yeah.
This week? Okay, so you've already done it. All right. So this is what you're supposed to do in lab. You're trying to find the specific heat of things. I don't know if they explain it to you this way or not, but it was comical, I'm sure. Okay. And it goes around and we get full credit. So, all right, now. Oh boy. All right. Okay, so what we're going to do is we got the little aluminum thing. All right, since this has already stolen all my thunder, which is only 0.1, I think it's 0.1 kilograms. No, 0.045 kilograms. And it's at 20 degrees. And it's at equilibrium with the water, which is equal to 0.2 kilograms of water, which it's at 20 degrees. And what they're going to do is both these, the final for the water and the final for the copper is going to be at 25 degrees. And so is the final, because when it reaches equilibrium, its final is going to be at 25 degrees also. All right, so here's how we do this. And here's the only way I know how to do this. Now, if you learn this in chemistry a little bit different, that's okay. The only way I know how to do it is using conservation of energy. What's gained is equal to what's lost. All right? So something is going to gain energy, and in this case, what's going to gain energy are the things that are cooler, and what's going to lose energy is the thing that's hot. Okay? All right, so we'll put the gains over here. Put the losers over here. All right. And what's gaining energy will be the 0.045 kilograms of aluminum times aluminum's 920 is its specific heat. So this is the C of aluminum times its change in temperature. It went from 20 to 25, so that's a positive 5. And plus the mass of the water, which is 0.2, times 4186, times its change, which is 5, and that'll equal the 0.15 times the C, which is what we're after, times its change in temperature, which is 75. Okay? Now, if I brought that loss over to the gain and was conserving energy, then the change in energy would equal 0, because everything's conserved. Then all of a sudden we'd have a negative here, which would give me the negative 75. But I just like to make everything balanced. Okay? Well, it looks like I've got all numbers in one variable, so that's pretty easy to solve. And once you solve this little algebra problem here, you wind up with C equals 390 for the copper. When you write a textbook and use that as an example, it'll come out nicely. I'm sure your lab thing probably we had some error. But that's okay. Oh, just a little bit? Some error, like 144%, those kinds of things. Just take the square, if you get big error, take the square root of it and say, there it is. I mean, if things go around and you get full credit, take the square root of your error. You're golden. Okay? All right. I didn't tell you that, but anyway. Okay. So that's specific heat. There's kind of a nice little specific heat problem. Now, I did you dirty, and I gave you one more homework assignment type thing, okay? And let's look at the hardest problem that you had was problem 34, which also looks at the latent heat of fusion. So before we go to that homework problem, let's do this. Let's look at this little graph which explains things. This is the way I have to see it, all right? Okay. Here we go. Let's just take an ice cube, okay? So let's take an ice cube, and it's here at negative 10 degrees Celsius. All right? And here's 0, and up here is 100 degrees Celsius. And here's the heat that I'm going to add down here. All right? So it starts off right here. I heat it up, and I heat it up, and I heat it up until it gets to 0. And right here it's specific heat in our joules thing for ice, I think it's 2,000 joules per kilogram degrees centigrade. Okay? And now, it gets to 0. It's not melted yet. All right? It's not like things, some things sublimate, like dry ice and things like that. Once they hit room temperature, they immediately go from liquid to gas without going to the solid stage. It's going to like that. But he starts doing this. He's going to stay at this temperature until he's completely melted. Now he's just a little bit of water, mostly ice, a little bit more water, more ice, half and half water, half ice over here. And this is latent heat of fusion. Okay? That's in its latent phase. Okay? This is going through a phase change. All right? It's going through its phase change. And its temperature stays the same during a phase change. All right? Then all of a sudden it's all water now. Not all of a sudden, it's slowly turned into all water. And then we go up. And here's where we get C equals 4186 joules, kilograms, centimeters, degrees centigrade, until it gets up here to 100 degrees, and then starts going through the same thing. It's going to go through another phase change. It stays the same temperature, some water, a little bit of steam, mostly water, half steam, completely goes to steam. Okay? Of course, there's some evaporation and stuff like that going on also the whole time. Okay? Which is a whole different, not completely different. It's in this chapter, but I didn't read it, so I'm not going to tell you about it. All right. I didn't go over it. So this is the latent heat of vaporization type thing. And I think that's 2010 or 2100 for water. Okay. Now then, and this is in joules per kilogram. No, that's not right. I'm sorry. That's not even close. That was the specific heat for steam. You're right. And the latent heat of fusion for water is 3.33 times 10 to the fifth, and it's just joules per kilogram. Okay? So in other words, to convert 1 kilogram of ice to water, I need to add this much energy to it and have it fully absorb it all. And then it'll turn into water. That's enough to break down those little lattice things and make it goopy. All right? Okay. All right, so armed with that, let's look at your problem 34, which is the trickiest problem that I gave you. All right? Which is the trickiest problem that I gave you of your homework to do. One of your problems is kind of funny. I didn't mean to give it to you, but it says there is problem 5. I wanted to give you just like simple ones like 2 and 3. If a person goes on a 1,500 big C calorie per day diet to lose weight, what is the daily energy allowance expressed in joules? 1,500 times 4186. I was kind of wanted to give you, but it wouldn't let me give you that one. So it made me give you a student ate a Thanksgiving dinner that totaled 2,800 calories. Okay, he wants to use up all that energy by lifting a 20 kilogram mass a distance of 1 meter. So he's going to do MGH. All right. Oh, that's kind of fun. Let's see how many MGH. Well, let's just do this problem because I'm curious. Somebody have their calculator? Somebody have a calculator so we can figure this out? Now remember, your things are going to change. They'll do you dirty. They'll say, oh, he ate 3,000 calories. He's going to lift 18 kilograms, 1.3 meters, something like that. So anyway, we're doing 2,800 calories. So for problem 5, we've got 2,800 calories. Now I'm doing physics on the fly, which is dangerous, times 4186 joules per big calorie. So we multiply that, 2,800 times 4186. What do we get? What's the first number? Dun, dun, dun.
11,720,800.
Okay, 11 million. We'll just leave it at 11 million. 11 million joules. Okay? Now, it could be. I always leave it when I'm doing you guys' homework. I always leave all my answers completely fat. I mean, just whatever it came out to be, and I just carry that number all the way through until the very end.
Well, that doesn't work.
It doesn't?
Not for me, at least.
Oh, really?
One of those not cool problems.
Oh, yeah.
Yeah.
Oh, yeah, that was the one about the clock. I've sent that one in.
Well, I've got a couple more for you.
Oh, really?
Yeah.
Oh, all the rest of them came out fine, I thought. They were okay, at least on mine. All right. Okay, now then, he's going to lift a 20 kilogram thing, a 20 kilogram mass, 1 meter. H equals 1 meter. Now we're going to count, we're going to say there's 0 work done when he goes back down because gravity's doing the work then. We're just, okay, 1, 2. How many times is he going to have to lift this thing to burn off 11 million joules? Well, let's see. How many MGHs do we have? Our MGH here is equal to 20 times 9.8 times 1. What does that come out to be? 196. So that's 196 joules for one lift. Take 11 million divided by 196. How many lifts is he going to have to do? And I don't think 59,800. It's going to take him a while. A long while. To work off. Wow. Just your brain working by itself for an hour, I think, burns something like 15 calories. So it burns a lot of joules off just sitting there. And when you're in this class, it's probably less, but All right, so there you go. All right, so that's how many lifts he's going to have to. That's quite a few. Okay, but now let's look at let's look at problem 34. Another one that I signed. I think you only have 8 problems out of this. There's one of them, and here's problem 34, which is the trickiest one. And what we're going to do is we're going to find the equilibrium temperature. Okay, I'll show you how to do that because this will probably be a test question. All right, something like this. If I take a 0.05 kilogram piece of ice, so here's what we're going to do. We're finding the equilibrium temperature of like 3 things brought into contact. All right? Okay, so here's what we got. I'm going to take some ice, which is 0.05 kilograms of ice, and the specific heat of ice is equal to 2,000 joules kilogram degrees centigrade. The latent heat of fusion is equal to 3.33 times 10 to the 5th joules per kilogram. Okay? And I'm going to drop this ice into 0.3 kilograms of water, which is at 25 degrees Celsius. Mass of the water is equal to 0.3 kilograms. Specific heat of H2O is equal to 4186 joules per kilogram centimeter. All right. And its current temperature, its initial temperature is 25 degrees Celsius. Okay? And it's also in equilibrium with this small little aluminum calorimeter thing, however you say that. And it's only 0.1 kilogram, or is it 0.01 kilogram? It's not very big. Or calorimeter thingy. Calorimeter. That's probably how you say it, calorimeter. There we go. I practiced all afternoon, I still blew it. All right. Of aluminum, and it's got a specific heat of 920. Okay. And it's in equilibrium with the water, and it's at 25 degrees Celsius too. It's not in this room, otherwise it would be at 30. All right, now, the ice has an initial temperature. It's at 0 degrees, so that's not bad. The ice is an initial temperature of 0 degrees Celsius. All right. After we drop this ice in, now this ice is pretty big. I mean, it's 2/3 the size. No, it's not. It's only 1/6 the size of the, for some reason I thought it was 0.2 kilograms. But anyway, it's only 1/6 the size of the water. I think there will be enough energy here. I will give you a problem so you don't have to analyze it at first. Because what if I had said I'm going to drop a 3 kilogram block of ice in 0.3 kilograms of water? Would anything really happen to that ice? No. The water would cool off pretty good, but the ice wouldn't melt, so we wouldn't have to change it. In other words, we'd just have to leave it at the latent heat of fusion. We wouldn't have to worry about any of this stuff. All right? But there is enough energy here that this ice will melt, okay? And it will cool the water down, okay? And so what we want to do is we want to find the equilibrium temperature. So what happens is, in this thing, so we'll cut off this part of this graph. And basically, the water is right here at 25. All right, the water and the aluminum. And they're going to cool down this way while the ice goes from here, starting here at the latent heat of fusion, and goes this way, adds all this energy, and then shoots up here, and they're going to meet somewhere right there. And this is my equilibrium temperature. That's what's going to happen. Okay? So what we do, gains equals losses, solve for equilibrium temperature, boom. All right, so here we go. So what's going to be gaining? The ice. What's going to be losing? The aluminum and the water. Okay? So let's erase all this, and let's just do the gains and loses over here. gains, loss, lose, loss, whatever, loose. Okay. So the ice is going to be 0.05 times 3.33 times 10 to the fifth. This is my MLV. M of ice times LV. No, LF. I did that this afternoon too. LF. Plus, it will turn into water. It will turn into water, so it'll be and we're going to say none of it evaporated. So it's going to be at 0.05 kilograms times 4186 times TE minus 0, which is going to be TE. Okay? So there's one variable, and that's the variable we're looking for. So far, so good. Things are looking good. Now, go to this side. Let's start with the water. We're going to have 0.32. It's losing energy. So it's going to be 0.32, or 0.3, what am I talking about? 0.300 kilograms times 4186 times 25 minus TE. Okay? Because it's lost that temperature. It's cooling off. Plus 0.1 kilogram of aluminum, 0.1 kilograms of aluminum times 920 times, again, 25 minus TE. Okay. Now we could be fancy with this side, and we could factor out the 25 minus TE, and I don't want to do that. Basically, the way I solve these problems, once I get down to this stage, I just start getting numbers. I don't try and get fancy and solve TE with any, no. I just start putting in numbers, okay? So when we start doing that, when we solve for T here, or when we're solving for TE, start putting in the numbers, I get 16,650 joules here, plus 209 times TE, right here, equals, now what I did was, little distributive property, multiplied this times 25 minus this times TE, and I wound up with, on this side, I wound up with 31,395 joules minus 1,256 times TE plus that 92 times 25 is 2,300 joules minus 92 TE. Okay, so what we do is we add the TEs to this side, subtract this joules here. See, it's going to work out nicely because we got 16,000 here minus this 31,000. I'd love when it comes out to be positive numbers. That means we've worked it correctly. Yes?
Under the gains, after you have the ice, first set of variables and weapons, plus what are those represent?
This guy right here?
No. Well, yeah, I guess that would be it. Yeah.
He's right here.
Yeah. What is that? Is that supposed to be the melted ice?
Yep. Yep. So he's gone from water times the, right.
So that's why you're using the specific heat of water with the mass of the ice, because it's going to okay.
Exactly. Did you all follow that, what she's saying? In other words, this is my ice thing. He's no longer ice after the end of this process. Now he's water.
Okay. But you're using
At
the mass of the
the mass
ice.
of the ice.
Okay.
Good question. Because that was kind of the whole crux of the problem, really. Okay? So, once we add all those to the other side and everything, I get 1,558 TE equals 17,045 joules. Divide it, and I wind up with TE equals about 11 degrees Celsius. Okay? expect something like that on the test, where we got a hot cup of coffee, except it'll be easier. It'll be something like we'll have a hot cup of coffee in a styrofoam cup, which is not like our aluminum thing here, which gives up heat. All right, styrofoam is a very good insulator, so it won't change. Its temperature doesn't change. Styrofoam's a great insulator because it's got all these air pockets in it and everything. That's what it's like, a thermal pane window. So that's why it works. Okay, so now we'll spend the next 10 minutes covering sections 1.4 and 1.5. Yes?
How come you use LF over there instead of C for ice?
Right here?
Yeah.
Because it's melting. It's changing phase. I'm adding energy to it. How much energy do I need to add to it to get it to turn into, because see all this energy, we're subtracting it out, so that's why. So it's changing phase on me. So that's why we started with the latent heat diffusion. Because I'm going to start out with, and I also could now, if this ice would have been colder, like at negative 10, if the ice would have been at negative 10, I would have done this. It would have been the mass of the ice times the sea of ice times, well, it'd be TE minus negative 10, TE plus 10.
Then you add that to the
Times the TE plus 10, right. And then we add that in there too, okay? So it's just going along the thing until there's an equilibrium place there. Good. All right. So now, heat. When we transfer heat, there's 3 ways we do it. There's three ways we do it. 2 require medium. And not Rosanna Arquette or whatever. Patricia, didn't see The Medium on television? Oh, that's for old people. Old people, I hate that show. Anyway. See, like, channels people. Something, I don't know. I just know it's been on forever, and I'm like, who watches this thing? But anyway. All right. But we're talking about mediums like substances, all right? A substance. Okay, so if we have a... so here's the first one. Conduction. I'm going to conduct heat right now. Got my hand, I'm warm. This thing's kind of chilly. I'm going to wait till they're same temperature. I'm conducting heat. I'm touching it. The heat from my hand is flowing into the whiteboard right here, and eventually it's going to be the same temperature, okay? Because that's conduction. Simple. That's what conduction is. Conduction is pretty much the way solids transfer heat. And I don't have any homework problems from this stuff, but the formula, because it is a heat flow type thing, so when things are flowing, it's a differential equation. Change in Q or the change in T equals some K, which is the coefficient of conductivity of the material, times its area. So that'd be the area of my hand here, all right, times the change in T, here's the differential on this side, divided by the distance it's got to travel, okay? All right? The classic case of conduction, take a hot poker, or take a poker made out of copper or something, which would be kind of a silly thing to make a poker out of because it gets very hot very fast. You put it in the fire. It's actually touching the fire. The heat runs up the poker and hits your hand. Hot. Ouch. Drop. Okay? That is conduction. The next thing, transfer heat. This is the way solids transfer heat. The next thing is convection. This is the way gases and liquids transfer heat. Okay, this is the way gases and liquids transfer heat. All right, it's not a very effective way. So in some ways it can be very efficient, very effective, but it's really complicated. I don't know how, I mean, I know the physical thing of how it works, but how to calculate that stuff, that's stat mech type, statistical mechanics type stuff. Right, Hal? Or Ting Yi? Am I correct? No? I'm even wrong? Oh, they don't know. Ha! Stumped them. No, they do. But anyway, all right. This thing is for like fluid dynamics type stuff, so it's very complicated. So basically, but convection is like, let's go to that same bonfire, all right? Fire's cooking, and I put my hands over it. That's the convection is the heat rising that I feel from the fire, because it's those air molecules are moving faster, okay, because they're hotter, so they got more energy, so they're rising, okay, and slower because they're less dense, right? Because they're spread out more, so that's why heat rises, because it's less dense than cold air. Then the cold air tumbles, and it gets by the energy from the fire, it gets hot, so it rises. So that's convection. Get that heat flow going like that. All right. Lastly, last but not least, is radiation. These two things require a medium. Radiation doesn't require a medium. That's electromagnetic spectrum. Those are electromagnetic waves, which we will talk about next semester in more detail. Okay? Basically, radiation from the sun. It doesn't require a medium. It's an electromagnetic wave that's traveling through. A classic example is those, like at Wendy's or something, where they've got the red lamps over the food that's keeping your fries nice and limp. Okay, all right. That's that infrared, which is heat, radiation coming out of those lamps. All right, in the form of infrared light, in that spectrum. It's in the spectrum of infrared. All right, and like in the, did y'all see Predator with Arnold Schwarzenegger? You remember the Predator picked up things by their infrared, so it picked up their heat they had. All right. But anyway, electromagnetic waves do not require a medium because there is no space is a vacuum. Like in the movie Aliens. When you're in space, nobody can hear you scream. Remember that? No? Come on. The movie came out in 79 or 80. Okay? I was in college. But anyway. All right. So with radiation, the amount of power. Now this is, oh, by the way, this whole part right here that we're talking about right now, this is all just kind of, we're letting physics flow over us here for the next like 3 or 4 minutes. In other words, it's really not that testable. I might ask you though, read in your book on greenhouse gases, because that's kind of the hot topic. Remember, and it's got a nice thing on how greenhouse gases work, what the greenhouse effect is. Okay? All right, but anyway, radiation has this formula right here. The average power of radiation, remember, this is another differential equation, basically, because power, of course, is joules per second, all right, is equal to the Stefan Boltzmann's constant, okay, which is 5.6, so that is 5.67 times 10. I've got it written down here somewhere. Where did I have it written down? I don't have this one memorized. Times 10 to the negative 8 watts per meter squared absolute temperature to the 4th power. So this comes out to be times A times T to the 4th. Remember, this is absolute power times this little e. I forgot the little e. Usually stick him in here or here. And this E is what is known. Did I write him down? No, of course I didn't write him down. But emissivity. I have trouble with these words. That's what E is. And he's between 0 and 1. And this is the last thing we'll talk about. Okay? 1, perfect absorber of radiation and perfect emitter. Black. a black box. All right, perfect absorber and perfect emitter. A black box. All right, this is completely reflects any radiation. Doesn't take on anything. Okay. All right, so here's a question. All right, this could be on a test too. This is a more conceptual thing. Which would you rather, you get kidnapped or you get whatever by some bad person, okay? It's a hot summer day. They give you a choice of which box they're going to put you in. A chrome box, which has an E of, like, let's say 0.55, or the black box, which has an E of 1.0. Which one's going to heat up faster? The black box. Gets very, very hot. All right? The chrome doesn't absorb quite as much. That's why the little boys, I think I've talked to you about this before, are little skater boys at the mall with their little insane clown posse black t-shirts or their Anthrax t-shirts, Megadeth, whatever, or whatever the band is now. I'm dating myself. Slayer. Slayer's still around. They're a thrash band in the 90s. No Slayer? No, our tankers in the brains, that's what they listen to when they're going through the minefield. But anyway, that's back in 91. But anyway, they're walking around on a hot August day with a black t-shirt and black jeans on. It's like, are you nuts? Wear white and your face will clear up. But anyway, so, look, you could. Our little skaters. All right, but anyway, but actually, they had an interesting picture of of a Bedouin in the Mideast somewhere, and it gets a little bit warm there, and he's actually wearing a dark burqa type thing, and might be going, I wonder why that is, because you think most of them when they're in town and stuff wear white. But sometimes the Bedouins wear the dark ones when they're out on the desert. It's because they don't have on anything underneath it. And what happens is, because it absorbs the heat, okay, it goes up, and because of convection, then that gets cool air coming up from underneath, from the ground. So it works like its own little cooling device type thing. All right? So that's why they're wearing the darker ones, because they do want it to absorb, and it emits just as much as it absorbs, and so it's going out at the top, and then it's drawing cool air up from the bottom, where the less dense air is from the desert floor. Okay, so, yeah, so I'm sure that was I'm sure they didn't they didn't write down that equation to figure that out. It was probably just by trial and error. All right. That's all we've got for tonight in Chapter 11. So, Chapter 11, the homework problems only go through 34. I didn't ask you anything about the conduction or the radiation questions. There are no problems on convection, really. But I might ask you on the test something about the greenhouse effect, just because you kind of need to know about it. Right? And I'll talk more about it on Tuesday.